Oopsies. So I hope you can see the slides already. And I will also have my laser point. Yeah. So today we will talk about these two-dimensional colloidal films. And so for the colloidal films, so I just want to make it so why we talk about these colloidal films. Yeah, so it's quite different from some how to say films which are from like polymer or brocopolymer. So the film we talk about today, it's made from the colloidal particles. Yeah, so that's why. So for colloidal films, actually they have some very special properties. And also for the methods for the preparation, it's also, there are some specific methods. That's why we talk about this. So for the talk today, I will first give you a general introduction just to remember you. Yeah. So what are the colloids? And of course, here the interaction of the colloids is very important when we consider for the preparation of the films. And of course, yeah, what kind of interaction you can use, yeah, to stabilize the colloids. So then after this short introduction, we will also go to details on the film formation procedure of these colloidal films and also the mechanism. So here's a deformation of this colloidal particle is one important procedure during the film formation, and we will also discuss about this, what is the mechanism behind it. And of course, yeah, so followed with this, we will discuss different methods. So I list some, yeah, so these are the most common used methods. You see there are quite some methods you can use to prepare the colloidal films. And here, of course, I will also give you some for each method, what is the advantage and what is the limitation of these methods, because later always depends on the application. You should choose the appropriate methods. Otherwise, it will be extremely difficult to have a nice, with good property of the colloidal film. And of course, I will also give you some example. So what we can do with these colloidal films, what kind of application they can have now. And in the end, so I will also give you a short summary and the future challenge or what we can do, like the further step on this topic. So just to remember you, so some basics or fundamental about the colloids. So I think you should already know, because colloids is really one of very, how to say, it's a specific topic, So the real expertise, of University of Potsdam, if we considering the chemistry or physics, to compare with other universities. So this colloid is also one of the strongest aspect for the research groups here at the university. So for the colloid, so first of all, you need to know at which size dimension it is. So normally it between so like a molecule level to of the sun. So then you will have some idea. So the typical size for the colloidal particle is around a few nanometer, then to a few micrometer. And due to their small size, they have very high or large surface to volume ratio. And very important property for the colloidal particle is, so when they are in the dispersion, they undergo the Brownian motion. And I mentioned this here because you remember we discussed in the very beginning how to measure the particle size of the colloidal particle. And here we normally use the dynamic light scattering. And the basic of the dynamic light scattering, we should assume so the particle should have the Brown motion. So if the particle are too big, they will not have this Brown motion in solution. then the DLS measurement actually is not suitable anymore, yeah, in this case, to determine the particle size. And of course, yeah, when we talk about the colloidal particle, we always need to do so stable dispersion. And in this case, so we need to know the interaction of the particles. And here, the balance, yeah, so there's attractive and also repulsive interaction between the particles. And the balance of this is very important here to keep a colloidal stable system. And for the attractive interaction, so it's based on the van der Waals interaction. And for the repulsion, so normally it depends. So if you have charged particle, then you have the electrostatic interaction. So this is repulsive. But we will talk about this in the next slide, because it's one of the most important here properties for the colloidal particles interactions. And so before we go there, I just want to give some terms, because sometimes, so even for my postdoc, yeah, they sometimes confused this definition. So what is the coagulation and what is the flocculation? So for the coagulation, so it means a kind of aggregation, what is irreversible. So it means when it's aggregate, you can never get it redispersed anymore. So it's called coagulation. But in some cases, actually, so when the particles are aggregated, it's still possible. For example, like salt solution, yeah. So if you add some salt, the particle aggregate. But if you add even more and more salt, at some time, so you salt will have a screen effect, then the particles are redispersed again. In that case, it's called flocculation. So just keep in mind, yeah. So these two definitions, so they are different. So then we should also keep in mind, because I mentioned already, so for the colloidal particle, the size can be around a few nanometer to a few micrometer. So then it means the colloidal particle are not only include the nanoparticle domain. Yeah? So actually it do, yeah, so bridge the molecule level to the macroscopic level. So just keep in mind, yeah. So because sometimes people are always mixed, yeah, the colloidal system is a nano system, yeah, but actually colloidal particle include, yeah, not only nano size, but also microscopic systems. And on the other side, so if we think about time region, so this is important for some spectroscopy measurement, because in that case, you need to know the time region of such kind of system. So for the colloidal particles, so you see they have the regions around 10 over minus 9 seconds to minutes. So this is a time region for the colloidal particles. So this gives you also the information how fast, yeah, if you want to understand the kinetics or mechanism, yeah, how fast your spectroscopy need to be. So yeah, just keep in mind, so the colloidal domain, not only, yeah, so just the nano size, so actually it's much broader. And you can find, of course, yeah, so this colloidal domain nearly everywhere, yeah, in our daily life. So from the simple like milk, or every day we push our teeth, yeah, so this toothpaste, and also to even more complicated biology like this blood cells, yeah, or this protein. Yeah. So they do have a very wide range of such kind of colloidal domain. So that's why it's really so versatile system, yeah, can have everywhere influence our daily life. And but here, of course, very important, of course, we need to understand the system, and we do need the colloidal chemistry and the colloid physics, yeah, to understand the principle. And so luckily, yeah, so colloid chemistry and colloid physics, these are two, yeah, so the most strongest expertise, yeah, of University of Boston. So because you know here we have the Max Planck Institute and also from Hoffa Institute. Yeah, so they do have the expertise on these specific topics. So as I promised, so we should understand the interaction between the colloidal particles when we talk about this system. And so I just remember you again. So here we have the attractive interaction. So this is normally based on the van der Waals interaction. And so this van der Waals interaction, they will try to pull this nanoparticle together, to pull the colloidal particle together. Yeah? And then if the particles, if they are charged, then we have this electrostatic repulsion. So you can also call it Coulombic repulsion. So this Coulombic repulsion, so they will try to keep the particle apart from each other. Then you do have the competition between the van der Waals interaction and the repulsion. And here, of course, depend on the system, but in most cases, so the charge on the surface, they are pH dependent. So here you can use pH to change the charge on the surface. And another very important point here is, so as I mentioned, so the salt concentration is also an important factor considering this Coulombic repulsion, because if you have a very high concentration of salt, in that case, you can screen the electrostatic interaction. So in that case, you can use salt to screen the Coulombic repulsion. And in that case, you can try, of course, to reach a kind of balance between the repulsion and the attractive interactions. And to be more, so too simple to understand the system in a real system, how you can stabilize your colloidal particle. As I mentioned, so you can be the charge system. In that case, so it depends on the electrostatic interaction. So it will be electrostatic stabilization for the colloidal particle. And in that case, of course, this Coulombic repulsion play a very important role. And because you have charge, so we have normally like the water is a solvent for such kind of colloidal particles. And on the other side, of course, you can also have steric interaction. And in that case, you will have a steric stabilization of the colloidal particles. And this steric stabilization can be based on like you have the polymer chains, and in that case, they are mainly based on the osmotic repulsion or entropic repulsion to balance these van der Waals attractive interactions. So just keep in mind, And so here, for the steric stabilization, so it can be used, so not limited in water, So this can be applied for all the solvents. And I should say, so now you see this is really simple, So these two concepts for the stabilization of the particles. But for the PhD defense, actually this question comes quite often. And I think this is also one of the most favorite questions from Professor Antonietti. But unfortunately, so not every PhD candidate can answer this question. But I hope, so if you will later have the PhD study here in Boston, and during your defense, maybe it's quite possible you also have the same question, so you can answer it, So this is really like two very basic methods for the stabilization. And so here, I just want to point out for the aqueous dispersions. And so here, of course, stabilization is very important during the storage. But in some applications, actually you do not need a stable particle. And this depends on the application. So in some cases, you should also use this principle, to destroy the stabilization of the system. So it's always like two sides, not only stabilize, but in some application, you need to destroy such kind of imbalance, the interaction balance. So with this, we can come to the main topic today. As we mentioned, so we will talk about these colloidal films. And of course, so the first question you will think about, so how this film, they can form. And if we look the scheme here, so I give you very simple, so scheme. So you have so wet colloidal solution on a substrate, then it start to dry. And then, so during the dry, so you will see, so the wet colloid droplets is like shrinking, getting smaller and smaller. You have like the dry surface of the film. And then in the end, the whole film, so it's totally dried. So the film then it's formed. And if we look at the system, of course, it's not so simple as it's drawn here as a scheme. So if we look at the cross-section of these films, we will see, so you have a kind of boundary. So this is the water and also air boundary. So you have the boundary. So, and here, so the water, the evaporation of the water, they are very fast at this boundary. So at this dry and wet boundary. And so here is where the drying of the film starts. So they start from the boundary. And another important point is, so during the drying, because you have the evaporation of water, then of course, so the evaporation of the water will bring the flux of water in the undried, so in the wet part of the particle. And this will give a kind of flux of the particle to move from the middle or center to the boundary. So actually you have a kind of movement here of the particle towards the edge of the film. So that's why, so this kind of flux of the movement of the particle, so will influence the final morphology of your film. And normally, so you will see a kind of film, and actually it's not homogeneous. So you will have, so at the side or the edge of the film, they are a little bit thicker. This is due to this flux during the evaporation of water. So particle, actually they will be pulled or moved at the edge of the film. So that's why you have always like a lot of particle or very concentrated particle at the edge of the film, but in the middle, a little bit thinner film in that case. Then of course, so this is the simplest system. Of course, if you have a very large surface area, in that case, you will have, of course, a kind of fluctuation of the total film. It may not be so homogeneous, and you have some places very thick film, some place a little bit thinner. And here, so I just want to say, so here, so water actually, so the flux of water, they play a very important role during the drying process. And this also actually will bring the, bring in the end, so the final properties of your films. So if we go deep into this evaporation of water, so if we go too deep of this problem, so as I mentioned already, so we have at the edge, so this is the liquid and air interface, so at the edge, so they will dry first, and then the particle, they try to move at this, and they will form a kind of reddened close packing of such kind of colloidal particles. And then, of course, then water will be further evaporate. And in that case, so the liquid magnesis at the top express. So here, yeah, they will have a kind of capillary forces. And this kind of capillary forces, they will bring so the film. So if the film is based on the hard particle, so the hard particle means the glass transition temperature of the particle is higher than the temperature you use to dry your film. Yeah? And in that case, of course, the film will be cracked, and you will see in the end, not a kind of a piece of film you can use, but you have a lot of cracks on the surface. And in the case of the soft particle, it means you have lower glass in transition temperature. And so in that case, so the particle will, due to these capillary forces, they will start to deform. And in that case, you will have a kind of deformed colloidal film in the end. So then if we go deep into the system, I show you how it works as a whole procedure if we go deep into it. So we have a kind of colloidal dispersion. So using water as a solvent, then water start to evaporate. So as we mentioned, so in the beginning, we will form a kind of close packing of the particles. And then water is still continue to evaporate. Then you will have a kind of deformation of the particle. Depends, of course, there's a transition temperature of the polymers. But if it's a kind of if it's so the temperature is lower, then you will have a kind of deformation of kind of particle. And then also, if you have a lower glass entrance temperature, then you have a kind of interdiffusion and the correlates of the particle, deformed particle. In the end, you will have a kind of homogeneous film. So this is a total procedure for the formation of the colloidal films. And here, very important, two temperatures. So one is the temperature for the deformation of the particles. So it's called MFT temperature. So here, the drying temperature should be higher than the MFT of this colloidal particle. Otherwise, it will not deform to form such kind of compressed layer or compressed formation. Another very important temperature is here. So the drying temperature of the film should be also higher than the glass transition temperature of the colloidal particle. Otherwise, so you form such kind of diclohedral structure, but it will not form a kind of homogeneous film, because in that case, because the polymer chains, so they are not movable, and you have still a kind of hard particle, so we always call it hard particle. And in that case, you will not get a kind of homogeneous film. And here, so that's why if you think about the specific polymer system, for example, for polystyrene, polystyrene has a glass transition temperature around 90 to 100 degrees. So depending on the molecular weight, of course, And so in that case, so if you prepare a film, so if you dry it at room temperature, you will never get a kind of continuous film, because the polystyrene particle is kind of, in that case, it's hard, it's a powder, because you will never have interfusion of the polymer chain in that case. So in the end, we will get a kind of powder-like film. But if you work with, for example, polybutene, they have very low glass transition temperature, much lower than the room temperature. And in that case, you will get a very nice, even sticky, actually, in some cases, and homogeneous and even transparent films in that case. And so as we mentioned, so one for the film formation, so the MFT is a very important temperature here. So I just go a little bit deep on it. And so what is the MFT, of course, yeah? So the MFT is a kind of a minimum temperature at which, yeah, so the polymer latex, yeah, they can form a kind of transparent film, yeah, during drying. And so here, so actually this also temperatures where you can get a kind of deformation of the particle. And so here's a modulus of the polymer, yeah, they should be less than 10 power of 7 par. Otherwise, so they cannot be deformed, because otherwise it will be a kind of glass, yes, a very hard polymers. Yeah? In that case, you will never get a kind of deformed polymer film. If you look into the definition, yeah, of course, yeah, so this MFT, so they have a kind of imprecise definition. So normally you can define it as a kind of a lowest temperature at which a polymer or solid portion of an aqueous polymer dispersion, they will self-coherence in the semi-dry state to form a kind of continuous film. And which in turn, yeah, so this film can, in some cases, can act as a binder for the rest of the solids, yeah, in the paint films. So, but this is a kind of imprecise definition. For us, we should know, so what we need to keep in mind is, so what is the temperature of this MFT? So normally it's within a few degrees of the glass transition temperature of the polymer. So normally it's like plus or minus, so in a certain range of this glass transition temperature. And of course, so this optical clarity, they can increase over time, with further currents of the particles. And for the same polymer, you can tune this MFT at a certain range. So for example, you can change the particle size. So by decreasing the particle size, you can also decrease the MFT. Here, so of course, so the driving force for this coherence is higher for small particles. And also for the small particles, so you have less light scattering. So this is for like the optical effect. And so there are also some groups, they actually have studied on this, so the influence of the particle size on the MFT temperature. So in that case, so this author, they use this acrylic copolymer latex particle. And they have the size, so they change the size of the particle from 80 nanometer to 500 nanometer. And they also studied the MFT. So they found they can increase, so the MFT temperature from 26 degrees Celsius to 36 degrees Celsius, so around like 10 degrees they can change. And of course, you can also, by mixing, so small particle with big particles. And in that case, they mix this small particle, which has the size around 60 nanometer, with a big particle, which has the size around like 450 nanometers. And with the increase of this portion of these larger particles in the mixture, they can also increase the MFT temperature of the whole system. So as a principle, of course, that's the same. So with the increase of temperature, you can increase the MFT temperature of the system. So of course, so sometimes you need to study the morphology of these films. And so for the morphology of the colloidal particle, so normally you should use AFM. The reason is why you do not use electron microscopy. The reason is because you can imagine, yeah. So especially when you have a kind of homogeneous film, and the gas transition temperature of this film is lower than room temperature, so you have a really a very homogeneous thin film. And in that case, if you do electron microscopy, like scanning electron microscopy, then you have a very flat surface or very smooth surface. In that case, because your particles are totally deformed, and you do have any contrast here, and in that case, actually, you can see nothing from electron microscope. And that's why, so you need to do AFM, because AFM can help you to get the contrast here. Very minor change of the height, they can see already very nice image by AFM. And this is the resolution of scanning electron microscope they cannot reach. And so that's why, so people not often use AFM to study the deformed particle, the dry film of deformed particles. So here you can see, so when it's dried, they will have this randomly close packed ring. And also you see, so the particle, especially at the borders, so at the boundaries, so they have a kind of a flattened boundary between particles. This is actually directly confirms this deformation of the particles after drying. So why? So such kind of deformation, they will happen in the colloidal system. And so here I just give you some detailed explanation on it. So if you have a kind of film made from this close-packed particle, for example, it from this FCC, so the face-centered cubic array of the particles. So it's close-packed. So for each particle, so here you will have actually 12 neighbors. So you see you have up here 3 points, and then you have 6 neighbors, and then of course bottom you have also 3. So you have like altogether 12 neighbors of each particle. And here it means you have contact here with 12 different neighbor particles, and all this contact, it will give a kind of force to which is associated with the deformation of the lattice during the drying process. And in that case, of course, depending on the number of the neighbors and the forces you will get during this deformation process, you will then form different kind of polyhedral particle cells. And here the major forces to lead such kind of deformation is from one is the capillary forces, and the second is from the surface tension. And so we first talk about the surface tension. So where are these forces coming from? That's why I will do together with you to do some calculation about the surface tension in the solution. So for example, you can imagine we have the latex particle dispersed in water. And so we have like number n, and the radius of particles r. And after the deformation or the coherence, you will form a kind of large sphere particle, which has the radius of r. Of course, in the end, you have formed a kind of very large particle. And you can calculate it. So what is the total surface area of this small welded particle, and also the surface area of this particle, which are made from this small particle coherence. So you will get the surface area of these two stages. And then you can calculate here. So after concurrence, what is the change here in surface area? And so here you can use this formula to calculate the change of the surface area. And of course, you can use this formula. I just give one example here. So if we have 1 liter of this colloidal latex particle, which have like the solid content around 50%, if we have originally this nanoparticle with a diameter of 200 nanometer, and the number, of course, we can also have, and then we can calculate it, yeah? So after concurrence, if we form from this 200 nanometer with a big, large particle, here we will have a kind of reduction or reduce of the surface area around 1.3 multiplied 10/4 square meter. So we have a huge change of the surface area after this particle concurrence. And the decrease or the change of this surface area, they are also related to the Gibbs free energy of the system. So here you also lead to the decrease in the Gibbs free energy when the particles are concurrence. And here you can use this equation to calculate it. What is the change of the Gibbs free energy if we have this particle concurrence with the system? And I continue with this example we have on last slide. So with this number of particle of 200 nanometer diameter, and this you can use as the interfacial energy, and then you will get a kind of minus 390 joule for the decrease in the Gibbs free energy. So this is quite a large of change in the Gibbs free energy. And here, one concept is very important because the energy, they have always a balance. So here we have reduced or gained the energy by reduction in the surface area with the particle deformation to form a kind of particle concurrence. And such kind of energy, what we gained from the Gibbs free energy actually is spent on the deformation of the particles. So so where the deformation forces come from, So actually, so it's from the what we gain from this decrease of surface area, and which also used for later, for the deformation of the particle. And so for the deformation, so it can be either elastic or viscous or even viscoelastic. So like both, it can. And also depend on the stage or the status of the particle during this deformation process. So it can be either drying sintering or wet sintering. So for the drying sintering, it means water, they already residues from particles when the particles are deformed. So it means you have a kind of deformation already at the dried state. In that case, so the reduction of the polymer air interfacial energy. So it's here. So this interfacial energy is a driving force for the particle deformation. And in the case, so if the particle, they are still, so the water, they haven't been evaporated here. So in that case, the reduction of the polymer water interfacial energy. So here in this case, so this will be the driving force for the particle deformation. So this is like two different here. You should know this. And another very important force for this particle deformation, as we mentioned, is the capillary force. And for the capillary force, actually, you can also calculate. So this is the pressure, yeah, if we have this capillary force. And so this is the interfacial energy, yeah, for water. And R is the radius of the polymer latex. And so you can calculate the capillary force in that case. And so for example, yeah. So here we use again the water, yeah, interfacial energy. And for the size of the particle around like 150 nanometer, so the capillary force, yeah, will be around 3 million Pascal. So it's really huge, yeah. So the pressure will, so this capillary force pressure will be also huge, yeah. That's why it will also lead to the deformation of the particles in that case. So here I just give you some typical values here, so you should know. So this kind of interfacial energy at which range, yeah. So this is just for your knowledge, yeah, how large the number should be. So then, so during this particle deformation, yeah, then you will form a kind of ordered structure. And in that case, if you want to form such kind of very nice ordered structure, you need very monodisc particles. So here, the requirement of the monodispersity is very important to form such kind of ordered structure of polymer latex films. And of course, yeah, so you also need to slow down the drying process. This will also favorable, yeah, to form such kind of ordered structure. And sometimes, of course, you can find here some defects on such kind of ordered structure, and often, so this happens where you have like the dispersity of your particles. So it means here you have like larger particles. That's why it will destroy, yeah, so such kind of nice structure. So that's why we need really monodispersed particle, yeah, to form such kind of ordered pattern of the particles. And this is also very important later. So people are also using this to form the colloidal photonic structures. And in that case, yeah, of course, this is even so have very critical on the particle size. It shouldn't be polydispersed. Otherwise, you can never get such kind of photonic structures. So if we talk about, especially on the hard particles, yeah, because this is you need need to know. So what is the maximum, yeah, of the density or the volume of the particle when you have close packing? And that's why we need to know a kind of phase diagram here. And so this is for the hard spheres. So if you have the volume fraction of the sphere particle, so when it's lower than 0.5, it's a kind of liquid colloidal particle. And when you increase the volume fractions, then it means you increase the solid content of particle. It will form a kind of crystal liquid coexistence in the system. And then it will start to crystalline. And when the volume fraction is larger than 0.58, you will form a kind of glassy phases. So this is like glassy phase of the particles. And then at kind of boundary, so this is around 0.6, you will have a random close packing. So remember this number here. This is often, yeah, so people, when they talk about this random close packing, they need to have the very high volume fraction of the particle, higher than 0.6. Then even larger, of course, you can have kind of solid, yeah, phase of this colloid particle, and the maximum you can reach is a kind of FCC crystal. So this is a maximum volume fraction, so 0.6 0.74 you can reach for this particle colloid. And so we go deep into this, So if this monosis particle, packing into this FCC crystal, so then you have a volume fraction, of 0.74. So this is the densest possibility for the hard space you can patch together. And if the particles are randomly packed, as I mentioned here, so if they are random packed, so normally they have the volume fraction around 0.6. And of course, here you can think about, you can actually fit the bonds between these particles, large particles, with some small particles. In that case, this is one possibility. You can increase the volume fraction of the system. And another way is, of course, if you have a kind of electric double layer, to prevent this contact of particle between particles, then so the volume fraction here will be lower than 0.6 to reach a kind of close packing here. So you will reach somewhere here. So these are also possible. So this is the example I want to show you. So if we have larger particles, if they are well ordered, close packed like FCC, you can have maximum 0.74 to reach this FCC crystal. But of course, you can use the small particles to fill in these voids here. Then you can reach a kind of such kind of binary particle system. And in that case, you can increase the volume fraction to get the packing fraction, so the higher volume fraction for the dense packing of the particles. And this also the some of the groups they have tried with this. So this is also AFM image. They're trying to prepare kind of a lattice film using the larger particles around 300 nanometer. And so then they filled this with small particles and to around 50 nanometer. And then you can see, so the small particles can fill this voids between and to reach a kind of high packing of the latex particle films. So then, so this is like kind of mechanism, how to form the polymer colloidal films. And then we can go through the different methods, how to assemble such kind of film from the colloidal particles. And so we will go through, so these methods today. And we start from the simplest one, so job casting. So for the job casting, it's from the word you can already know. So you apply a job of your colloidal solution, then drop it on a planar surface or planar substrate, and then let the solvent evaporate and the film will form. So do very simple, you just like job casting on it and then let it dry. And the advantage for this method here is you can, so of course, using the spherical or electrostatic stabilization of the particle to preventing the aggregation of particles. Because here, if the particles are already aggregate in the solution, you'll never get a kind of homogeneous film. And here you, of course, can using different flow mechanism to remix the particle during the film drying process. And on the other side, and it's also very important to improve the vetting. So vetting means how good the solvent, what your particle are dispersed on with the substrate here. because if you have a very high contact angle here, it will also difficult for you to have a homogeneous covered film on the substrate. So you should try to improve the wetting to increase the interfacial area between the job and the substrate. Here, so the negative effect or the backdrops when you prepare a kind of film based on the job casting is, so if you increase attract the interparticle forces, so you of course will have a kind of aggregation in the system. And on the other side, and the de-wetting, so of course it's not what we would like to have, because the de-wetting will result in the shrinking of the contact area between the droplets with the substrate. And on these cases, you will have kind of all inhomogeneous disperse of your film on the whole substrate. So that's why you should always considering when you do the job casting, so to have a positive effect to get a kind of homogeneous film. I give you also one example using the job casting. So this is a causal particle based on the polystyrene as a core cross-linked polynippon. And this particle can be synthesized by using different surfactant. Then you can get either positive charge microjoule particle or negative charge microjoule particle. And so the particles with different charge, depending on the substrate you use, you can get a kind of homogeneously deposition of this particle on the substrate. You can see from the SEM here. And from the film, so this is a photo of the film. So here, due to this order structure, so you can get a kind of erased fiber from the film deposited on the substrate. And for the job casting, one classical problem is covering effect. This is the most classical problem caused by this job casting. So covering effect means, so during the drying process, you have the edge of the job, which become pinned to the substrate. And on the other side is capillary forces. They want to bring the particles from the metal to the edge of this drying edge when the water evaporates. And then after evaporation, of course, so you have the high concentrated particle at the edge along the original job edge. So that's why you form a kind of covering, we call it so here. And these authors, they trying to solve this covering effect, and they found, so if they use such kind of ellipsoid particles, so you use anisotropic particles, they will overcome this covering effect and to form a kind of homogeneous deposited film on the substrate. And they think this is because of the anisotropic shape of the particle, they will deform the interfaces between the particle and the solvent. And so in that case, they will produce a kind of strong interparticle capillary interaction. And also, so the shape of the particle, they can provide a way to control the deposition particle and without change any, so you do not need to modify the solvent or modify the substrate. So this is one of the easiest way you can overcome this covering effect. Another example for this job casting is you can also to form a kind of colloidal crystals or colloidal photonic structure using this simple job casting method. But in that case, as I mentioned, so you should control the weight of the formation of your crystal and how to slow down this formation rate. Yeah, so you should slow down the evaporation of the solvent, of course. And so that's why these authors, they modify the way they put the substrate, and this is the colloidal dispersion of their particle, into a kind of semi-closed setup, because here then they can control the humidity. So in that case, they use nitrogen gas with ethanol vapor to control the humidity of the system, and with centrifugated ethanol vapor. So here, because ethanol can condense on the edge of your suspension, in this case will help to wetting the liquid onto the glass substrate to have a kind of a thin film spreading, so homogeneous spread on the surface. And so such kind of wetting process, they will help to form a kind of homogeneous films on the surface. This you can see also from the imaging here. And of course, you can calculate here what is the formation rate for such kind of crystals. And of course, yeah, so this is rated with, on one side, the concentration of the particle you use, the size of the particles, and also the evaporation flux of the system. So the evaporation flux is exactly as they are trying to play here. So by using this ethanol vapor. And so you can see this also they have tried to tune or change the spreading and drying process of the suspension, and they can even control like 2 layers of this particle or 3 layers or 4 or 5. So you can get a kind of multi-layer crystal film formed on the substrate. And dot plating, so this is also one of the favorite tools to deposit colloidal particles. And this is also for the industry. They quite often, so this is often used by the industry to form a kind of film, and they can really control the thickness of the film on the different flat substrates. So normally you drop the colloidal solution on the substrate, then using the dot plate to go through, then let it dry, so you can get a kind of dried film. So then the advantage for this method is, so you do need a lot of material. And of course, this is cost efficient. And they can also use for very large surface areas. And by control the concentration of the particle, you can also control the thickness of the film. And of course, yeah, sorry. And of course, you can also pre-treat the substrate surface, and you can also control the roughness of your surface. So I also give you one example on this. So these authors, they modify this dot plating and just put one such kind of plate, which is viscous on the surface of these colloidal particles. And in that case, because you will move this dot plate, and they will form a kind of pressure on the both sides. So you will lead to a different kind of this pressure on both sides. And this external pressure will help to form a kind of colloidal crystal film. And so you can see from the imaging here, they can form very homogeneous film based on these colloidal particles. And also, depending on the concentration of the particles, so they try different kind of concentration of these silica particles, and they can also tune a little bit the thickness of these films. So this is another example. This also uses docked plating, but using these copper indium cerium nanocrystals. So this is one of the often used film for the solar cell application. So that's why, so these authors trying to make the film on the ITO-coated glass substrate. And so they have tried using the different concentration of these nanocrystal particles. And they can, so by tuning the concentration of the particles, they also can tune the thickness of these films. And you can see also, so in that case, so by this docked plating, they can have a kind of homogeneous crystal film and without any pinholes on the surface. Because these pinholes, of course, is very bad, if you think about these solar cell applications. This will lead to a kind of defects on the devices. And another method we will discuss today is, of course, the spin coating. So spin coating, I should say, is one of the most often used method in the lab. So this is often actually what we use, So this is lab-based methods. And so here you have a kind of, so the process, so you put a drop of your dispersion on a substrate. So the substrate actually is rotated at certain speed. And then, after the rotation, so the film will, like the colloidal particle will spread on the substrate, and then meanwhile you will dry the film and form a kind of homogeneous film on it. So that's why, so using spin coating, normally you can get a very homogeneous, very thin film. So this is a method if you want to make very thin films. And for the control of the process, so here you can think about, of course, so on one side is the viscosity of the solution is very important to the film formation during the spin coating. And another one, of course, so the speed for the spinning will be also very important. If you speed too fast, of course, you will, your dispersion on substrate will be all thrown away. You do not have any on the substrate. But when it's too slow, it will, like itself will dry it. Of course, it will also make inhomogeneity in the film formation process. And of course, you can also play a little bit with these spin coating methods and to get a kind of multi-layer structures. So for example, you can like first using one latex solution. So on the substrate, then you rotate, let it dry. Then you repeat with another kind of a secondary dispersion. So you can get a multi-layer structure to repeat this process. So this is also possible. But here I should say, so this is trickier because each layer will play important role for the final property of your films. So for the spin coating, so actually this is one of the first technology, or the first one people use to close a kind of two-dimensional colloidal crystal films. And of course, this can also allow, so very easy. So the spin coating is quite common method which are available in the lab. And also it can be used as a, so it depends on the substrate and also the spin coater. So you can also use for large area deposition of the films. And also, yeah, so if you want to get a kind of long-range ordering of such kind of colloidal films, you should, yeah, trying to improve the wetting, so the wettability of the colloidal dispersion with your substrate. So here, so you can think about, yeah, so the wetting property of the dispersion with the substrate, actually not only for the spin coating, it's also very important for other methods, yeah. So here I give you one example. So these authors, they also using the two-step, yeah, spin coating to get a kind of binary colloidal crystal. So you see the first here, the first step spin coating use the big particles to form a kind of two-dimensional colloidal crystals. Then in the second step, they're using smaller particles, and then to let the small particles, of course, depends on the difference, yeah, of these two size during these two different spin coating process. So they can form different kind of two-dimensional binary colloidal structures. So this is also one of very clever methods. Of course, yeah, so you can also using this spin coating for some smart polymers. So here they use this thermoresponsive polymers. So it's a core particle, and you have gold as a core, and the cross-linked polynipon. So polynipon is temperature sensitive. And then they use also spin coating to form a kind of thin layer of such kind of polymer latex particles. And very interestingly here is, so you can, yeah, so during this polynipon, so you can form a kind of ordered structure. And because polynipon is temperature sensitive, so if you increase the temperature, so polynipon, they start to shrink. And in that case, it's like you see a kind of shrinkage of the particles. So here is like fully covered. And when we have the shrinkage, yeah, you see like only the gold cores on the surface. So this is a very nice method. And of course, yeah, then you can also see, because gold is plasmonic, yeah, they have this plasmonic absorption. So you can also observe these optical, yeah, properties of such kind of film, yeah, on the substrate. And this is a very good way to form such kind of thermal responsible, yeah, thin film on substrate. Another method is the deep coating. And deep coating is one of the most often used method if you want to have order structure, so the colloidal photonic colloidal structures. And for the deep coating, so you see you have a container with a lot of dispersion. Then you put your substrate here into the dispersion, and then you will pull it out here very, very slowly. Normally you need overnight. And so that's why for this deep coating, normally you need very long time. So normally like days, sometimes even weeks, yeah. And also you need a large number or large quality of your latex particle. So that's why it's quite waste, yeah, of your particle solution. And so this method actually, so of course you will get nice structure based on this method, but unfortunately for industry application, so it's a kind of impossible, yeah, because it's with too much, and you can see, so if you need to pull out of your substrate, yeah, you should not disturb it. This is a big problem, because we also did this in our labs. If in the daytime, you can forget it, because someone nearby, so neighbor labs, if they close the door very heavily, then you will see later on your substrate like a line of, you see clearly what happens, what neighboring labs they are doing. Yeah? So that's why you need an undisturbed environment to do such kind of measurement or such kind of deposition. And this is the principle for the dip coating. So for the formation of the film, actually it should be similar. Yeah. So you have a kind of substrate, and then due to the solvent evaporation, you have bring a kind of capillary force on the surface. So you have the particle. Yeah. Like the capillary force will bring the particle. Yeah. At the edge of the film, and then it will form a kind of homogeneously deposited colloidal particle on the substrate. And depending on the concentration of the dispersion you use for the dip coating, of course, you can form either so this single layer film or multi-layer films. So here's a parameter which you can use to control the film. So on one side, of course, is the substrate and the solvent, what you can use. And also here, the angle you tilt the substrate, yeah, it can be also used to control the final structure of your latex films. And of course, so the evaporation rate is also very important parameter for you to control. So here you can either control the temperature or the humidity of the system, yeah, or the drying process. And of course, so another very important parameter, of course, the concentration of the colloids. And so here, this I will not go to detail because a little bit complicated for you maybe. So you can actually know well, yeah, there are already well-defined way for you to calculate the thickness of your films by this dip coating process. And so it depends on you have a kind of a wet coating layer or the dried film layer. So they can calculate it precisely the thickness of the final colloidal film based on this spin coating. And the parameter, yeah, you can control here, of course, yeah, it's similar as we discussed, like the tilt speed, the concentration of your particles. So the solvent you use, yes, these are all the parameter you can tune. And of course, yeah, so here's one example. You can change the concentration of your dispersion for this dip coating, and then you can change, yeah, so the coverage of the film in the end. Another very often used method. So this is Langmuir blockade technique. And this is often used for a thin layer or monolayer film, yeah, based on the air-water interfaces. So the principle of this method is like this. So you have a kind of water or liquid, and between you have two barriers, and then you add your dispersion, latex dispersion in between. Then you move these two barriers together. Then due to the change of the surface tension, these molecules or the latex molecules, they will form a kind of monolayer. And meanwhile, if you tilt here your substrate, like from and up, you tilt the substrate up, then it's formed, yeah, the thin layer will formed on the substrate on it. So this is one way you can make the film. On the other side, of course, you can also do not use this tilting during the move of this barrier. You can just move the barrier and measure the surface tension of the system. So here is the surface tension, yeah, when you move these barriers. So you can always very well, yeah, control the whole process. So this is like when they are too far away from each other, so you do not have interaction with each other. Then when they get close, we'll see the increase of this surface pressure, so interaction. And then when they form a monolayer on the surface, so then you see a kind of tandem concentration. And here, you know, I have formed already a kind of monolayer. Then you can, of course, you should have experience on it. Then you can use a substrate to go through the solution and then to pure this thin layer or monolayer from the liquid air interfaces. So, of course, so this is a good method if you want to have a kind of monolayer film. But as you can see, as I explained how you work on it, so it's can be worked only for very small amount, small area substrate. And for the industry application, of course, it's also too complicated. So you can never use it for industry application. But this is a good way if you want to, for some lab experiment to get a thin film method. And so here is also, they try to use this method. So they use a silicon nanoparticle again. And in that case, so you can measure the surface tension during the Langmuir-Brocknet technique. So then you can, of course, also measure the surface concentration of these particles. When you pull them together, you know the change of the concentration. You measure the surface tension. And then in that case, of course, you can calculate the density of your film. So density of the film is the mass of your particle on the surface area. This is all well known. So you can calculate the density of the film. And with this, of course, so you can to recalculate it, the concentration in the dispersion in the end. And so here you can also see, so by this Langmuir-Brocknet technique, you can also form such kind of ordered two-dimensional structure. The last method I want to talk with you is also a kind of often used layer by layer assembly. Layer by layer assembly, so it's also easy. So you have a dispersion of your colloidal particle and you have a substrate. And then due to the different electrostatic interaction, so if you have a negative charge substrate, then you put positive charged colloidal particle, then the positive charged particle will absorb onto the negative substrate. Then you pull it out, wash it, so you have already one layer ready. Then you put it into, because now you have the positive charged particle on the surface, so you can put into a negative charged molecules or other particles, then it will deposit again on your positive substrate. And then you put out and wash again, then you come back again. So this is like called layer by layer. Of course, you need to repeat this procedure for several times to reach a kind of thickness of such kind of complex film. And so here, the interaction you can use, so what I introduced is this electrostatic interaction you can use, of course. And of course, you can also use other interaction to use layer by layer assembly. For example, you can use this metal ligand interaction or hydrogen bonding or some supramolecular inclusion. So there are different interaction you can use for layer by layer assembly. But of course, here you also see, so it's not so straightforward. And you do need to treat the system very carefully. And it's time consuming because you need to make different deposition methods. So that's why this is also often lab used method. And for the industry application, it's too complicated. Anyhow, for the lab experiment, this is a good method, especially you want to study the interaction of different charged particles. And so, for example, so these authors, they also trying to form such kind of colloidal films by oxidively charged particles. So they use polystyrene particles. So One is like positive charge, another is negative charge, and then they want to form that kind of a binary opposite charged polystyrene particles. And of course, yeah, so what they found is very interesting. So if you remember in the very beginning, so the salt concentration, they play quite an important role because the salt can screen the Coulombic interaction. It means so the salt can control this thereby so screen length of your surface. So that's why so these authors, they do this deposition method at different salt concentration, and they found they actually can change the thickness of these particles. So this is a very nice, of course, for the fundamental understanding of this salt-leaded screen of the surface. So with this, so I want to also give you some example what you can do. Of course, so you can using this method and to form a kind of nice film. Depending on the application, you can choose different colloidal particles, and to form the colloidal films based on this particle, and to use them at different applications. So, for example, you can form that kind of photonic crystal based on the colloidal films. And in this case, so the Bragg diffraction, this is fundamental how you can tune the photonic band gaps for such kind of colloidal films. And if you understand, of course, this Bragg diffraction, so this is the equation, how you can tune these photonic band gaps, then of course you can have a huge or the possibility to tune the color of your final colloidal films. And of course, so here, important, of course, you should know, you tune the band gap. So for the visible means, so you change the color of the film. So this is the way how you understand the system. And of course, so here you can have different application for such kind of photonic crystals based on the colloidal films. This is also one example. You can even using the responsive polymer materials to form such kind of photonic crystal structures. And of course, then because you use the solvent responsible polymer, then they are responsible for different films, then you can change the band gap or change the color of the film by using different solvents. So these authors, they trying to then deposit so this film in different solvents like water, ethanol, acetone, you see a continuously change of the color of these polymer films. Another example is, so of course, you can also play more complicated things. So you can deposit these plasmonic nanoparticles. So they're also using these Kochel microgels, and to deposit it onto the films. And here, very interestingly, is they combine the deep coating with the growth of these gold particles. So they into the one step, then during the deep coating process, you will till the substrate from the gold close solution, and then you can form a kind of gradient of the gold particles, depending. So if you how long it will be totally peeled out from the gold solution. And in that case, you will have a very nice, you see from this photo, so the change, so the gradient change of the color, which is responsible, of course, to the size of the gold nanoparticle. And if so, here is like the slowest, so the lowest part, so it means you have a very big particle can be growth in the end. You can have a very good way to control this graduate plasmonic array by combination of this film formation with the growth of the particles. So this is the last example I want to show you. So these authors, they also use these films, and they also use silica-coated particle. And during the self-sampling, they deposit gold onto this photonic crystal structure based on silica nanoparticles. And of course, gold is very well known for this surface-enhanced Raman spectroscopy. And by deposition of this gold nanoparticle into this ordered crystal films, they can use a kind of surface application, which also show very good enhancement, so the surface enhancement for the Raman spectroscopy. So in this case, of course, you can get a kind of composite film based on this method. So then we can come to the conclusion, and also as I promising you, so of course, so there will be some challenge on this field. And here, of course, the new approaches for the preparation of colloidal particles still need to be developed. And here, of course, the main point is how you can develop such kind of methods, which can be also used for not only for the lab side, but also for the industry application. And of course, so here you can always combine the film formation with the external field. This is in the moment not well started yet. And also, of course, you can combine the film formation with the precursor of the colloidal particles. And this is especially important when we think about the perovskite solar cell. Now it's kind of very hot topic, And here people do understand, so because you use a precursor of this perovskite and how you can control the film formation, meanwhile, with these precursors on the surface. And another very important aspect, of course, so you can use a novel colloidal system for the film formation. And here, instead of this spherical particle, anisotropic colloidal particle will be also very nice system to understand. So if you change the shape or morphology of the particle, what will happen during this film formation process? And on the other side, of course, you can use this stimuli responsible system to see, so if you change temperature, pH, or salt concentration, if something will also happen for your film formation. And there are a lot of possible applications for the colloidal films. So on one side, of course, so for the energy materials, so all the electrodes we prepared for this battery or the supercaps application, actually we use this dot plate deposition methods. So in that case, you can have a large size of such kind of film, which can be used as the electrode for battery applications. And the same for this solar cells. So you can use a spin coating or inkjet printing to film, prepare the film for the cell applications. Another aspect, of course, is photonic crystals. So this is very nice for this optical application. And as understanding of this formation process, it will be nice, of course, to have a kind of operando or in situ methods. So you can, during the formation of the film, you can combine with the in situ characterization methods to understand the whole process. And of course, so the theory, so the simulation is also an important aspect to understand the mechanism behind the film formation process. So this is like the future challenge, yeah, for this part. And yeah, of course, yeah, then with this, so for the better understanding, you can come back again, yeah, to design your system and to have new approach, yeah, for the preparation of these colloidal films. So with this, so I have gone through all the slides today. So is there any question from your side? So I do not hear there's any further question. So then I would wish you a nice weekend. So it seems we will still have such hot weather during the weekend. But next week will be better, So but you can still enjoy the sunshine. So maybe also go for swimming during the weekend. And then we will see next Friday. So then have a nice weekend. So
Sure. Thank you.
bye.
Bye.
Thank you.